I already told you what white noise is. So white Gaussian noise is a white noise which is also Gaussian. So I can say that x of t in R is white Gaussian noise if 1 is Gaussian, random process. 2, mean of x of t is 0 for every t, and correlation C or covariance R x t comma s equals Rx of t minus s equals n naught over 2 delta of t minus s. That is, the correlation function depends only on the difference, and thus it is White's and stationary, right? And it is a delta function. There's nothing new here. It's a second example that is of interest that I would like to spend some more time. Example 2. And we will call this the Wiener process. Or else it's called the Brownian motion. Okay, so this is an important random process. We want to describe it through some kind of motivating example, and then we will see kind of its precise definition. So here's the motivation. Imagine that we discretize time. So we have 0, delta t, 2 delta t, and so on, all the way to t plus delta t. Okay, so we split the time into intervals of t over delta t intervals. Okay. And let's define a discrete time random process as follows. x0 is 0, start with 0. X at time delta t, so I already defined it at these points. Okay. X of delta t is some Gaussian random variable that I call n0, which actually happens to be x0 plus n0. Then x of 2 delta t is at this point is a random variable that is n0 plus n delta t. So the sum of two Gaussian random variables, which is x delta t plus n delta t. x3 delta t is going to be the sum of three Gaussian random variables, which is actually x of 2 delta t plus n delta t. And I go all the way like that until I get to x of t plus delta t, which is n0 plus n delta t plus all the way to n of t, okay, which can be written as x of t plus n of t. Where in all this n t's, that is n0, n delta t, n2 delta t, and so on, are IID random variables that are all normal 0 sigma squared delta t. That is 0 mean random variables with these variables. Do you see what I have created here? This discrete time random process at every instance is the sum of all previous elements of this random process plus one additional Gaussian component. You see that? Starts at 0. At delta t is n0, so it's Gaussian. At 2 delta t is the sum of n0 and one more. At 3 delta t is sum of this 3, and so on. Okay? What do you expect this process will look like as time goes by? In terms of its variance, it increases because I'm adding up more and more Gaussian random variables of the same variance. What happens to IID Gaussian random variables? The sum of these. What is the variance of the sum of Gaussian random variables? Of IID. The variance of the sum of IID random variables. It's a sum of the variances, indeed. Okay? It's a sum of, so somehow this process increases in variance. What about its mean? 0. Okay? So it's a process that, although has 0 mean, that is equally likely to be. And by the way, what are all these quantities? Sum of Gaussians. So they're Gaussian random variables. So it's a Gaussian random process where at every time you can think of it as having 0 mean, that is equally likely to be positive or negative. Okay? But as time goes by, its variance increases. Yes? Okay. Not only that, at every time t, you can think of this process as what it was before, xt, just the previous one, plus a little bit more of a additional randomness. This kind of random processes are called random walks. So where I am at time t plus delta t is where I was at time t plus some variation, the step I took between t and t plus delta t. So this step can be positive or negative, and it has a distribution here. And it's independent of everything that I have done in the past, because this nt is independent of all the previous steps. Okay? So this is what we call a random walk with independent increments. Right. Let's try to figure out or write down what we have discussed so far about this process. What is mean of xt? Is mean of, I can say, n0 plus nt, which is linearity of expectation. 0 plus 0 is 0. Okay? What is mean of xt squared? Well, it's mean of, maybe I can write this as a sum, summation I equals 0 to t plus delta t over delta t of ni. Okay. Expectation of summation I equals 0 to t over delta t of ni squared. How do we solve this problem? So what is the mean? We write this square as a double sum, summation over I, summation over j of ni and j. And then we pass the expectation inside, summation I, summation j, mean of ni and j. And then we split it into two parts. The I and j are equal, so that's mean of ni squared, plus summation I, summation j, I not equal to j, mean of ni and j. What can I say about that? Ni and nj are two Gaussian random variables that are independent because I and j are different time indices. So this is mean of ni times mean of nj, which is 0. And what about that? This is the variance of each ni, which I told you, it is sigma squared delta t. Times how many they are, t over delta t of them, sigma squared delta t gives me sigma squared t. And now you see why, as we said, the variance of this process increases linearly with time as time goes by. Okay? Because it's the accumulation of all these independent steps up to time t, infinitesimal steps. Okay? Let's try to find together r x of s comma t, which is mean of s, xs, xt. And let's take to make things easy, the case where t is greater than s. So here's what happens. Here's my idea. The process, right here is xs and right here is xt. The process x, the random variable xs depends on all the noises n that came before it. Okay? While xt can be thought of as xs plus all the noise components that came after. Now I know that these components and these components are independent. So I will use that to write, this is mean of, xs I leave it as is, but I write xt as the sum of xs plus a summation of ni's, I going from s over delta t plus 1 to t over delta t. Okay? And now I can split that into mean of xs times xs is xs squared plus mean of xs times the summation over I of ni. I equals s over delta t plus 1 to t over delta t. And I want to ask you about this one first. Well, that's easy. Mean of x squared, we found it, is sigma squared times s. But what about that? What can you say about this expectation? And I want you to see this diagram. xs is a function, actually the summation of all these independent n's that were added up to that point. And this is the sum of noises that come right after that point. But these two quantities are independent, right? And they are sums, they're Gaussians, they're actually correlated, independent, everything. And so this is mean of xs times mean of summation and so on, which is 0. Okay? So what did we find? Rx of s comma t equals sigma squared s when s is smaller than t. And what do you think it happens when s is greater than t? By symmetry. Huh? Sigma squared t. So I can write this as sigma squared times the minimum of s comma t. Right? That's the correlation function. Is it a wide sense stationary process?
No.
I have already a yes and a no. Is this a wide sense stationary process? Is this a function of s and t, or can I write as a function only of s minus t or t minus s? Let's take an example. Suppose s and t are 1 and 3, or 11 and 13. What's the difference? 2. What's the difference? 2. So, but the mean of s and t here is 1 and 11. So this function for the same t minus s has two different values. So this cannot be written as a difference between s and t, but you don't need that. Because I want you to understand these things more intuitively. What did we just say about this random walk? That as time goes by, although its mean is 0, its variance increases. So the statistics of even x of t do not remain constant with respect to time. Okay? If this were to be a wide stationary process, since the correlation is only a function of the difference, then Rx of 0, that is mean of x of t squared, should remain constant throughout. But it doesn't. Okay? In fact, it becomes more and more and more kind of bigger. It becomes bigger, right? Why? Because it's accumulating a lot of randomness as it goes on. Alright? So this is not a wide sense stationary process. If anything, you can think of this as the evolution of a stock price, right? So as time goes by, its volatility increases because the time today is what it was before, plus, I don't know, some independent things that happen in the market between the closing of last time and today, okay? And what happens next time and next time and next time is all this addition of these independent components, so the volatility, the variance increases. Okay? All right, so this is, all right, so let me just define now the Wiener process. Process is the above as delta t goes to 0. Okay? So that's why we describe this discrete time process, and now we take delta t to 0. Now you might say, what's going on here? As delta t goes to 0, then every little component here, noise, component that I'm for a certain number t, I will add a lot of them. a lot of these components, right? Because now delta t is very small, more and more and more components. But each component becomes smaller. Why? Because each component, as you can see here, was defined as a Gaussian random variable with variance sigma squared delta t. So as delta t becomes smaller, each component becomes smaller. So the combined effect of this, of having a lot of them, but each one of them smaller and smaller and smaller, is the Wiener process. Okay? There's something very interesting here. Okay? And this is what makes the Wiener process very, very, very interesting. Look, if I tell you that, that's a general question. If I tell you that a random variable x represents voltage, okay, and it has some variance 4, okay, so this variance relates to voltage, this number 4. What are its units? I'm asking you. Voltage squared. So if you wanted to tell me something about how wide, how broad this range of voltages are, then you wouldn't use sigma squared, you would use the standard deviation sigma, right? Because this has units of voltages, correct? So you would say that roughly the variance, the range of these values is 2, not 4, the square root of that, in terms of volts. Look at what is the range of values of each individual little component n delta t that we add here. The variance is proportional to delta t. And so, in terms of the actual units of what we measure, this is proportional to square root of delta t. Okay? So look what's going on here. We are adding many, many, many components, but each one is not consistent, is not scaled by delta t, it's scaled by square root of delta t. Okay? So that the variance squares with delta t, and because the variance are adding up, the variance is the one that has the sigma squared t, as we proved here, as we showed here. Right? That's something to think about. That it's these smaller components do not scale as delta t, but as square root of delta t. So, although I can say that, and I can be done with kind of the engineering way of approaching the Wiener process, there is an axiomatic way of stating it. So I will just state it in an axiomatic way. A Wiener process is defined. So a random process x of t, t in R, is said to be a Wiener process if the following are true. First, it's Gaussian. 2, mean of x of t is 0 for every t. 3, the correlation function is sigma squared times the minimum of s over t. And 4, x0 is 0. This fourth sometimes is omitted, but so that we start always with 0. Okay? So if you use this axiomatic definition, you can derive all the results that we derived earlier just by looking at that. So let's see some consequences of this definition. So from now on, I'm not going to be using the previous way of how I constructed it as a limit, but I'm going to be using this. Okay? So, consequences of definition. Okay, what is mean of x of t squared? Well, by definition is Rx of t comma t. Rx of t comma t, which is sigma squared minimum of t comma t, which is sigma squared t. That's exactly what we found before. Second, suppose s is smaller than t. Okay? And look at, here is s and xs, here is t and xt. And I want to look at xs and xt minus xs. And I want to take the correlation between these two random variables, xs and xt minus xs. What am I expecting to find here? Remember, from the construction of this process, XS depends on all the noises up to that time, and the difference of this and that depends on all the noises over here, but the noises were IID. And so what do I expect of these random variables? To be what? Since they are also jointly Gaussian. Independent and zero mean, right? And so what is this? Zero. Let's see if the axiomatic definition gives me that. Well, this is mean of xs xt minus mean of xs squared. This is Rx of s comma t minus Rx of s comma s. This is, if s is smaller than t, this is sigma squared times the minimum of s comma t, right? Which is s, minus sigma squared the minimum of s comma s, which is s. So this is indeed 0. Okay? So the axiomatic definition recovers this result. So since xs and xt minus xs are jointly Gaussian and uncorrelated, then they are also independent. Processes for which, let me put it this way. Suppose this is xs and this is xt. So this is xt minus xs can be thought of as the process increment in s comma t. Okay, and xs can be thought of as the process increment in 0, s. Well, let's put the open. Okay. So processes for which their increments over non-overlapping intervals are independent are called independent increment processes. And they are very useful in modeling. Have you seen any other process with independent increment property? The Poisson. The number of arrivals here and there are independent random variables, right? So the Poisson. So these are called independent increment process. Here's a third property. That's interesting, we're going to get back to that. Take some time samples, T1, T2, T3, all the way to Tn that are ordered, okay? And I want to ask the following. What are the statistics of the random variable x Tn, so less than xn, let's say the CDF, condition that I give you the value of xtn minus 1 equals xn minus 1, and xtn minus 2 equals xn minus 2, and all the way to xt2 equals x2, and xt1 equals x1. Okay? In other words, this is a process here, and I have t1, t2, t3, all the way to tn, and I'm asking, what is the distribution of this random variable xtn, condition that I know the specific realization of all these. How can we solve this problem? How will you go about solving this problem? Don't try something smart, like vanilla flavor probability here. How do we do it in principle, without having to do something really, really smart and fancy?
You can use the conditioning rules, your really only interested in the last increment from Tn-1 to Tn.
Okay, that's a bit fancier than I expected. I would go with something much simpler. I would say this is a Gaussian process, which means that all these n random variables that I design are jointly Gaussian. Yes? And so all I have to do is to find what is the conditional distribution of one Gaussian condition on all the others. I know what this is. It's a Gaussian. I have solved this problem in the past. Okay? And I know the statistics of these n random variables that are Gaussian. How do I know them? In order to know the statistics of n jointly Gaussian random variables, or in other words, of a Gaussian random vectors, I need two pieces of information. The means, they're 0, and their covariance matrix, which I can find. For instance, what's the correlation between xt1 and xt2? By definition. Rx of t1, t2, which is sigma squared minimum of t1, t2, which is sigma squared times t1, right? So I know that. And I can, any pair of these I choose, I can find their correlation, so I can build a correlation matrix. So in principle, I can say this is a Gaussian distribution for sure, with a certain mean and certain covariance matrix. Okay? And the covariance matrix should depend on the values of these quantities. Right? So at first glance, it seems that the statistics of xtn depend on all the numbers that I will tell you, my observations from the past. Yes? But now comes another observation. Tell me, what was the observation that you made?
That only the most recent one matters.
That somehow xtn, recall, can be thought of as this random variable plus this increment here. Okay? Now, anything that happens before that and that increment here are independent. Okay? So somehow knowing all these numbers, all these values, xn2, x2, all the way to x1, doesn't give me any additional information. Right? Because this is just what this was, plus something independent of everything else. So if I were to write down this correlation matrix, and I do it, like in brute force way, I will see that all these numbers are irrelevant in my calculation. Okay? So let me just say in English what that says. The statistics of the future conditioned on the present and the past depend only on the present. That is, if I give you the present, the future and the past become independent. Does that make sense? Or in other words, it's only the last value of the observation that you give me that matters. Now, this process are called Markov. This is an important program that we will study in detail towards the last part of this course. Okay? Markov processes are the most useful processes in modeling probability. Okay? So I will just write it like that. Dot, 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 and I ask you to fill in the blanks. Okay? This is the probability. xtn less than or equal to xn, condition only on xtn minus 1 equal to xn minus 1. Okay? So, condition on the present, xtn minus 1 equals xn1. The past, xtn minus 2, xtn minus 3, x2, x1 is independent of the future xtn. Okay? I want you to do it in a kind of to prove this on your own, like write down the precise proof. Okay, finally, the fourth property. Suppose t is greater than s, again, this is t, this is s, and I want to calculate that. tell me what is this that I'm trying to calculate and give me a motivation for that. Why would I want to calculate something like that? Mean of x of t, the mean of this random variable x of t, conditioned on all observations xl up to this point. What is this? Why would this be useful? For forecast. Ah, how do we call that? Estimation, we call it in our language, right? We want to estimate this variable in the future, conditioned on all measurements up to that point. What do we know about optimal minimum mean square estimation? What is the optimal minimum mean square estimate of one random variable conditioned on its observation? The conditional mean. That's what it is. The conditional mean of xt, conditioned on all the observations. Okay? So how would I use it, or why would that be useful? The forecast. I want to forecast the weather at time t based on all my observations at time s. Okay? So, what do you think this is? Well, let me put it another way. Think of xt being your earnings when you go to the casino at time t, and you want to estimate your earnings conditioned on how much you have in your pocket up to time s. That is, you're playing roulette or you're playing a game. Let's say a fair game. So I look at my watch, I'm S, and I say I have $100 in my pocket, all my winnings. What's my best estimate for what I will have in my pocket an hour from now? What do you think?
Still $100.
$100. If I play a fair game. That is, if I play a game where winning or losing is kind of equally likely. Okay? If that's the case. Alright, so I claim that for this random process, this is equal x of s. Processes for which this is true are called martingales. Okay? And there are processes where this is greater or equal to xs, which is called some martingales, and less than or equal to xs that are called super martingales. In any case, martingales are very important processes in modeling things like stock market or games where you have this property where the best estimate of the future is the current value. Not the current expected value, the current value. Okay? The latest estimate that you have, xs. Let's prove that. Mean of xt given xl from L between 0 and S is mean of xt given xs. Hey, do you believe that? And why? Markov property. We said it earlier. Given the present, the future is independent of the past. Okay, so I can drop everything else. Alright, but let me write this as mean of xs plus xt minus xs. I can always do that, given xs. Then linearity of expectation, mean of xs given xs, plus mean of xt minus xs given xs. What is this? Xs. And what is that? Independent increments. The increment from here to there is independent of the random variable xs. Okay? So this is mean of xt minus xs. Because I can drop the conditioning. But what is mean of xt minus xs? We have said that this is a zero mean process. Zero. So we proved it. Yes? No? Maybe? Okay. I was hoping I would get the chance to discuss one application that is called the matched filter. I give you a demo, but I will do it next time. Let's say the following now. We're finishing this chapter, so next time I will discuss this application when we finish this chapter. The next chapter is technically the most demanding chapter in 501, okay? Because we will discuss limits of random variables, okay? Now remember, what is a random variable? A function. So somehow we will be forced to discuss limits on functions. It's not clear what that means. There are a lot of interpretations. So we'll see a lot of different definitions of limits of random variables. Why is this important? It's very important. Because this will bring about two of the most important and celebrated properties of random processes, what is called the central limit theorem, that is, if you add up a lot of random variables and they're independent, no matter what they are, eventually you will get a Gaussian, but in a very certain sense that we have to discuss. And the other is what is called the weak law of large numbers, or the strong law of large numbers, that says that the statistical mean of a random variable can be found by adding up a lot of realization of this random variable. That is, the arithmetic mean and the statistical mean are the same in some very well-defined term. Okay? So in order to introduce these very deep ideas, we have to get into what is called limits of random variables. That's why we define 1, 2, and infinite random variables. Now that we have infinitely many random variables, let's say sequences of random variables, I can say what is the limit of that as n goes to infinity, okay, or as t goes to infinity in continuous time. So just brace yourselves for a couple of weeks. Then we will kind of cool down for the end of the semester. Okay? So I understand that this is technically a bit challenging, so I'm fully aware of that, and so I'm letting you know.